Hello there, this is Jude Socrates. Welcome to where we will talk about the integral test as it applies to infinite series. We'll basically cover section 2D from my textbook. And again, if you don't have a copy, just go to the description and look for the link to Dropbox where you can download a copy of the textbook. All right, so let's go there and see what it is all about. But before we do that, let me tell you that we are going to discuss or incorporate into what we're going to talk about today the concept of improper integrals, which we saw in video 16. And in order to prove the theorem, we're going to need the monotone convergence theorem from our previous video, 2 videos ago in this series. So if you've forgotten about improper integrals, maybe look over that for a little bit. All right, here we go. So when we first talked about infinite sequences, we said that many times you can create a sequence by letting it be the value of a function defined, let's say, for all real numbers, or at least for positive numbers. And all you do to get the value of the sequence is to plug in the value of n, and that will get you the nth term of the sequence. Okay? So this function f could be defined for all real numbers, or more specifically to an interval of the form from k to infinity, closed on the left at k. Now, the integral test talks about the infinite series as well as in an improper integral. The test says the infinite series, summation of n from k to infinity, converges if and only if the improper integral from k to infinity of this f of x converges. All right? So in order to decide whether or not this infinite series converges, we will look instead at the improper integral from k to infinity of the function f of x. Okay? So let's go back to our workroom. We're going to do an example, and then we're going to see why does this integral test work. All right, here's our example. Consider the infinite series, summation of n equals 1 to infinity of 1 over n to the 7/5. Okay, so that's kind of weird exponent, but it is what it is. So what does this mean? We'll start at 1. So 1 over 1 to the 7/5 is just simply 1. And then we are going to add the next term, what happens when n equals 2. So 1 over 2 to the 7/5. And then we will go add 1 over 3 to the 7/5. All right, and so on and so forth. So we know what an infinite series is. We're just going to keep adding these terms one at a time. Now, Maple can do this for us, of course, except it's not always good with finding the exact sum of an infinite series. Sometimes it knows the answer, sometimes it doesn't. So let's just add the first 10 terms. Let's make Maple add the first 10 terms for us. What are we going to get? It's about 2.129. Excellent. Well, you probably don't have Maple, so let's go to GeoGebra, and I'll show you a command that will help us compute these partial sums. You already know how to make a spreadsheet, but this one, if all you need is a partial sum, then this next command that we're going to learn about is going to be just perfect for you. All right, here we are in GeoGebra, and the command is the sum command. Okay, now it was giving me some issues earlier, so I hope it works now. So in the sum command, you have an expression. So let's just put n. And then the index is the same variable n. And we will go from 1 to 10. Oh, okay. It's behaving for me for a change. So this means we're adding 1 plus 2 plus 3 plus 4 all the way up to 10. The answer will be 55. You don't believe GeoGebra? You can add it all together by hand. All right, so this is the sum command, and let's duplicate it. And whoops, I'm sorry, duplicate, where are we? Duplicate input. Okay, here we go. Go away, and what we will do is we will look at our example which is 1 over n to the power 7/5. Whoops. Shift 6. What did I do? Shift 7. Haha. All right. 1 over n to the 7/5. And we're going to get, boom, 2.12972. That looks familiar. Let's go back to our workroom. Memorize that number. Abracadabra, we get the same answer. All right. So we can get the partial sum of the first 10 terms. And while we're at it, how about the first 100 terms? Okay, so let's save this answer. We know that this is our S10. Our series starts at n equals 1. This is the 10th partial sum. How about 100 terms? Excuse me. And we get 2.71. Ooh, that's like another 0.6, right? That's a big jump. So this is S100. Let's go for 1,000. I hope it doesn't hate us. Let's see. Put another 0. And, ooh, wow, that's another big jump. So obviously just adding 10 terms together does not get us very close to whatever the exact sum of the series is. Okay? At this point, we don't even know if the series converges or diverges. So from the looks of it, I'm not feeling very confident. Okay? However, the theorem says that this series converges only if and only if the improper integral, which involves the parent function of this series, converges. So in our case, our function is going to be this term, except instead of n, we replace n with x. Okay, so it's just 1 over x to the power 7/5. And we are going to compute an improper integral. So I already prepared the skeleton of what we're going to do, because it's a pain to write that out. I have it handy. There we go. We want to integrate that improper integral. So what does this mean? Well, we are going to, there we go, excuse me. Let's see, there we go. And let me put that here. Okay, now I'm happy. Okay, so this is x to the power negative 7/5. So find the antiderivative. Negative 7/5 plus 1 is x to the power negative 2/5. And we divide by negative 2/5. So it means that we multiply by negative 5/2. Okay. And we evaluate this from 1 to infinity. Okay. So infinity, 1 is safe. We're not dividing by 0. What about infinity? So this is really 1 over x to the power positive 2/5. So maybe let's change this to a reciprocal. 1 over x to the power positive 2/5. Okay, now we can see what's going on. As x gets bigger and bigger, going to positive infinity, 1 over x to the 2/5 is getting smaller and smaller. Right on? So what's going to happen? At infinity, that's going to 0. So we're going to get 0 minus negative 5/2. And when x is 1, we'll get 1 to the 2/5, which is simply 1. All right, so the answer is simply 5 over 2. Okay. Maple, did we do it right? Did we? Let's see. We get 5 over 2. Okay, thank you for confirming. So the integral test says that this, I'm sorry, let's go back to the infinite series. Whoops, not all the way there. Let's go right there. Summation 1 over n to the 7/5. We integrated 1 over x to the power 7/5, and we found out that it converges. So according to the integral test, the infinite series summation 1 over n to the 7/5 also converges. All right, so we demonstrated that theorem, and now let's see why it's true in general. Okay, so let's review. This improper integral converges to some limit I, some number I, if the proper integral from k to b of our function has a limit as b gets bigger and bigger as we push b to infinity. Okay, so we learned how to do that in that video on improper integrals. We did it to our example. We had our antiderivative, x to the minus 2/5 times minus 5/2. And in general, we're going to need an antiderivative. Okay, to make this test work, we need the antiderivative or an antiderivative for a function. And we go from k to infinity. What that means is we push the limit as b goes to infinity of f of b, and then we subtract the value of the antiderivative at the beginning, start of the interval, at k, right? So now, since our sequence is positive, let's make sure that we mention that as part of the conditions of our integral test. Our terms are positive, so the function where it comes from must also be positive. And furthermore, it should be a decreasing function from k to infinity. And that part is quite important. So let's make sure that we see that condition. The function f of x must be decreasing. Our function was 1 over x to the 7/5. Of course, that is a decreasing function. Okay, so now, because it is a positive function, there are two choices, okay? Either this improper integral converges to some limit I, or it diverges to infinity, right? Because the function is positive, what we are integrating will give us bigger and bigger areas. So you either reach a limit or your limit is positive infinity. In other words, you diverge to positive infinity. Let me also say that in general, your function doesn't always have to be monotonic decreasing on k to infinity. Maybe it increases for a while. Let me use my right hand. Maybe it increases for a while and then it becomes decreasing. Okay? Now, why is that just as good? Well, an infinite series adds up terms from a1, a2, a3, all the way, keep going. Okay? But if the first few terms are increasing and then it gets decreasing, well, you can ignore the first few terms and just think of the terms where they are now forming a decreasing sequence, right? And then you can just add on the beginning terms that you initially ignored, right? So this is going to be a common theme in the other 5 theorems that we're going to talk about in terms of the convergence of a series. There will be conditions there, and we're going to relax those conditions by saying it should eventually have this property. Whatever it is that we're talking about should eventually have this property. In this case, our function, where a sub n came from, must eventually be decreasing. Okay, so when we had our 1 over x to the 7/5, it's easy to see that that function is monotonic decreasing because we have a positive power of x in the denominator. So it will be true also for 1 over x squared, let's say, a much nicer exponent. But if you don't have such a nice function, you can always appeal to the first derivative test to find out where your function is decreasing, if eventually it's going to be decreasing. Take the first derivative. If the first derivative is negative on some interval from d to infinity, then your function is monotonic decreasing on this interval. All right, so here's the proof of the integral test. The idea is to interpret the term a sub n as the area of a rectangle. So here is here are two identical diagrams, except for these two rectangles over here. They look the same, aren't they? Yeah, but they're not in the same place. Okay, so our sequence comes from f of x, which is supposed to be a monotonic decreasing function and positive, right? So it's always above the x-axis. All right, here's 2. So that dot there is 2a sub 2. There's 3. That's 3a sub 3. There's 4. There's 4a sub 4. All right, so what I did was I created this function and I plotted these 3 points. And then I made 2 rectangles. Okay, so this height here represents a sub 3. Because that's the value of your function at x equals 3. But this rectangle goes from 2 to 3. So the base is 1. 1 times a sub 3. The area of this rectangle is a sub 3. Okay, now, I hid this rectangle and I made another rectangle. So we start with the same corner, 3a sub 3. But this time, I go to 4. Okay, so the width of the rectangle is again 1, and the height is a sub 3. So the area of this rectangle is also a sub 3. It's exactly the same rectangle, except it's moved now to the right, right? It's actually drawn over here between 3 and 4. Okay, so here's the rub. Look at this rectangle here. And it is entirely below the function between 2 and 3. And that's because your function is monotonic decreasing. So the value of the function at the right endpoint is the smallest possible value of that function between 2 and 3. Now let's flip the script. So this time, our rectangle is to the right of 3. Between 3 and 4. This time, we're looking at the function between 3 and 4, not between 2 and 3, right? So between 3 and 4, again, 4 gives you the lowest point. This time, 3 is the highest point on that function, because again, it's decreasing, all right? So what does that mean then in terms of an integral? Remember that an integral, a definite integral, represents an area under a function between a and b, right? So let's go back over here. The function f of x between 2 and 3 is entirely above this rectangle. So that means that the definite integral from 2 to 3 of your function should be bigger than the area of this rectangle, because this rectangle is a part of that definite integral, which we're going to see in a minute. Similarly here, except it's the opposite. The function is now entirely below a sub 3, except at that left endpoint. So the definite integral between 3 and 4 is going to be smaller than the area of this rectangle. You see how the definite integral is going to be inside that rectangle. So the area under that curve is going to be smaller than the area of that rectangle. All right, so there it is. Here's the definite integral from 2 to 3, and it includes that rectangle. So that definite integral is bigger than the area of that rectangle, or another way to say it is that the rectangle's area is smaller than the definite integral from 2 to 3. Over here, the rectangle is bigger than the definite integral between 3 and 4. So the area a sub 3 is at least the definite integral from 3 to 4 of our function. Right? So of course, clearly, we can generalize these observations with these two inequalities. What's going on here? We have a sub m. 3 appears in the upper limit. 2 is, of course, the integer before 3. So a sub m is at most the integral from m minus 1 to m. 3 there, 2 there, 3 there. M minus 1, m. Okay? But, of course, we have to make sure that we're already within the terms that are needed in the infinite series. So this is true when m is bigger than k. And similarly here, we have a sub 3, at least the integral from 3 to 4. So this time we have a sub m and the integral from m to m plus 1. 3, 3, 4. M plus 1. Looking for patterns. So this area of the rectangle a sub m up to here is at least the integral from m to m plus 1 of f of x dx. Before we look at the proof for the integral theorem, the integral test, finish the proof, we're about to use the monotone convergence theorem, which I mentioned at the beginning of the video. So I am saving you a trip to an earlier video by reviewing what does the monotone convergence theorem say. Suppose that we have a sequence, a monotonic sequence, which means it is either increasing or decreasing. If the sequence is bounded, then the sequence converges. However, if the sequence is unbounded, then the sequence diverges to infinity or negative infinity. So remember that bounded means that there are two numbers, little m and capital M, where the terms of the sequence are between little m and capital M. In other words, the terms are restricted to be between the smallest value and the biggest value. Another way of saying this theorem is that a monotonic sequence converges if and only if it is bounded. So we're about to see how this theorem applies to the integral test, because we need to look at the partial sums of our infinite series, just like we did in the example, where we did summation 1 to 10, 1 to 100, 1 to 1,000. Let's go back to the proof. All right, we are ready to finish the proof. We created some inequalities involving integral from 2 to 3, 3 to 4, but our improper integral goes from k to infinity. Okay, so we're going to have to put those building blocks together, and we know that we can do that by the additivity property of definite integrals. If we're integrating the same function from 1 to 2 and from 2 to 3, and we add them together, well, that's the same as integrating the function from 1 all the way up to 3, right? So we don't have to stop at 2 over there. We can go all the way to 3. So of course, if we add one more term, if we go from 3 to 4, then we can integrate from 1 all the way to 4, right? So that is what we're going to use to make the proof work. Okay, now, I mentioned partial sums. So going back to the infinite series, we want to create the sequence of partial sums for this series. So remember that the first partial sum sk is simply the first term a sub k, which is of course positive. To get the next partial sum, Sn plus 1, you take the last partial sum, S sub n, and you add the next term, which is an plus 1. But an plus 1 is positive, so to the previous partial sum, we're adding a positive number, which means that the partial sums are increasing. Okay, monotonic. Our partial sums are monotonic. Increasing, we can apply the monotone convergence theorem. We saw that in our example. A sub 10 was 2 point something, 2.3 something maybe. A sub 100, a little bit bigger, 2.7 something. A sub 1,000, I'm sorry, S1000, it was about 2.9. Okay, so the partial sums are getting bigger, and of course that's because we keep adding 1 over n to the 7/5, which is a positive number. So our partial sums keep getting bigger and bigger. Okay, so we have two possibilities. Your improper integral either converges or diverges to infinity. Right? So let's look at the first case where our improper integral converges, right? So that means that the limit of the definite integral from k to b as b goes to infinity must converge to I. All right, so now we will show that the sequence of partial sums are bounded above. We can find an upper bound for that sequence of partial sums. So what does it mean again? Sn is ak, add ak plus 1, ak plus 2, all the way up to an. Okay, but what did we say? We said that, let's go back to where it was. We had these two inequalities. AK is less than or equal to AK, integral from k minus 1 to k. Oh, but wait a minute. Our domain starts at k. So we can start at k plus 1. AK plus 1 is less than or equal to the integral from k to k plus 1 of our function. And we keep going. So here we go. AK plus 1 is less than or equal to the integral from k to k plus 1 of our function. The next term, ak plus 2, is less than or equal to the integral from k plus 1 to k plus 2 of our function. So replacing each of these terms by the corresponding definite integral gives you a bigger sum, right? Because this is bigger than this. I'm sorry, this is smaller than this is smaller than this, and so on. Okay, but what did we say? This goes from k to k plus 1, and then k plus 1 to k plus 2. Keep going. N minus 2 to n minus 1, n minus 1 to n. So it's the same as the definite integral from k to n of our function. All right, so if that might be confusing you a little bit, here's a diagram that will explain it. If k starts at 1, and we go up to 12, n equals 12. Okay, so we want A1, except this rectangle has height A2. This rectangle has height A3, and so on. The last rectangle has height A12. Okay, so the green region here represents A2 plus A3 all the way to A12. And as we can see, those rectangles are below the function from 1 to 12. Okay, so that diagram illustrates that inequality when k is 1 and n is 12. All right, so of course, a1 is missing, but we know that the integral is at most the integral from k all the way to infinity, because we're integrating only up to 12 in that diagram. If you integrate all the way to infinity, if you push further to the right, then of course you get a bigger number. But we know that this improper integral converges to I. So this tells us that our partial sum is less than or equal to ak plus the integral from k to n, which we said is at most the integral from k to infinity, which is at most I. So therefore Sn is less than or equal to ak plus I. This is an upper bound for our partial sums. Haha. The sequence of partial sums is bounded above by the monotone convergence theorem, since our partial sums are bounded below by 0. Then the improper integral converges. Then by the monotone bounded convergence theorem, the infinite series also converges because the partial sums converge. All right. So now let's do the flip side. What happens if the integral diverges to infinity? Okay, very bad. So it means that the limit as b goes to infinity of the definite integral from k to b must be positive infinity. Okay, but now we also saw that the same partial sum, ak plus 1 all the way up to an, ak is now at least the integral from k to k plus 1 of the function. ak plus 1 is now at least the integral from k plus 1 to k plus 2 of the function, all the way up to the integral from n to n plus 1 of the function. But again, we don't have to compute those separately. We can go from k all the way up to n plus 1. Okay, and again, if that confuses you a little bit, here's another diagram. Okay, so this time we can start at A1 instead of A2 in the previous diagram. Here's A2, here's A3, except now the last rectangle, we are using the height at 11, okay, because we're using the left endpoint to be the height of our rectangle. All right, so now these rectangles are bigger than the definite integral from 1 all the way up to 12 of our function. All right, so we can see now that the partial sums are at least the integral from k to n plus 1. If we take the limit as n approaches infinity, well, this goes to infinity, so therefore Sn must also go to infinity. So therefore, our infinite series must also diverge to positive infinity. All right, so putting them together, these two cases, we can say that our infinite series converges if and only if the improper integral from k to infinity of the parent function also converges. All right, so this was our example. We have summation 1 over n to the 7/5. And we looked at the improper integral and we're like, oh, great. We were able to compute it and say, nice, the limit at infinity is 0. So 1 is no problem. The improper integral converges. So let's take a look at a related infinite series. We're going to flip that fraction. Instead of 7/5, we're going to do 5 over 7. Whoops, not 5 over 5, 5 over 7. Okay, so now we have n to the negative 5 over 7. We want the improper integral from 1 to infinity of 1 over x to the 5 over 7. Okay, so negative 5 over 7 plus 1 is positive 2 over 7. So we will get x to the positive 2 over 7 divided by 2 over 7, so that's 7 over 2. So we have 7 over 2, x to the positive 2 over 7. All right, so there is no need for us to flip anything. Unlike before, the exponent stayed negative. This time it became positive. And we're going to 1 to infinity. Going from 1 to infinity. Okay, well, x is getting bigger and bigger. X to the 2 over 7 is still getting bigger and bigger also. All right, so unfortunately, that improper integral diverges to positive infinity. Okay, so this series now diverges by the integral test. And in fact, we can be more specific and say diverges to positive infinity. Okay, it's a bad series. So what's the pattern here? Whoops, clicked on the wrong sidebar. What's the pattern here? 1 over 7 to the 7/5 converges, 1 over 5 over 7 diverges. What about something a little bit simpler? What about 1 over n just to the power of 1? 1 over n. Okay, so we were using the power rule earlier. The power rule does not apply to 1 over n because what we want is integral from 1 to infinity 1 over x. Okay, so everyone should know that the antiderivative is a natural logarithm. Absolute value, but everything is positive. We're going from 1 to infinity. So we want ln of x from 1 to infinity. And of course, what happens to ln as x goes to infinity? That will diverge also to positive infinity. Okay, so pattern. 1 over n to the 7/5, no problem, converged. 1 over n to the 1, just 1 over n, diverges. 1 over n to the 5/7 also diverges to positive infinity. We have the same conclusion for our summation 1 over n. Okay, so why are these two bad, but 1 over n to the 7/5 is good? 7/5 is bigger than 1. So when we do the power rule, we can still see the computation here, because negative 7/5 plus 1 is still negative. That negative exponent means that the x should flip to the denominator with a positive exponent. By doing that, as x goes to infinity, the limit is 0. When the exponent is less than 1, then the power rule, negative 5/7 plus 1, that is now going to be a positive exponent. It stays in the numerator. It doesn't get flipped. All right, so let's generalize. So here we go. When we did improper integrals, we did integral of 1 over x squared, 1 over square root of x, and so on. And we noticed that for some of them, the improper integral converges, the improper integral diverges, right? But in general, all of them have the exponent in the denominator. We have a positive exponent, right? So these are all decreasing sequences. So the P series that they create all come from a parent function, 1 over x to the p, which are positive and decreasing. So therefore, the integral test applies to all of them. What did we observe? Well, for summation 1 over n that diverges, summation 1 over n to the 7/5 that converges, summation 1 over n to the 5/7 that diverges. So let's generalize. All right, so we can now generalize. If p is a positive number, then the p series, summation n equals 1 to infinity of 1 over n to the pth power, converges if p is bigger than 1. 7/5 bigger than 1. When we add 1 to negative 7/5, that is still a negative number, so the exponent has to be flipped to the denominator where it becomes a positive exponent. But the p series diverges to infinity if p is between 0 and 1, not including 0, of course, and to the 0, that's just 1 over 1, boring, and also divergent. But p can also be equal to 1. We said that summation 1 over n diverges. These p series also give us a counterexample for the test for divergence. We said that if the limit is 0, if the limit of the terms is 0, we cannot decide if the series is convergent or divergent. And now we know why. For both summation 1 over n to the 7/5 and 1 over n to the 5/7, both of those terms go to 0, except one of those series converges and the other one diverges. Right? So major rule. If the terms go to 0, there is no way that you can conclude right away that your infinite series converges or diverges. The numbers are getting smaller and smaller. It doesn't mean that the partial sums are approaching a limit. Now we see that that's true, or rather there's a distinction. if we apply the integral test. Okay, so the idea that we use to prove the integral test will also allow us to control the error that we get when we approximate the exact value of an infinite series using just a partial sum. All right, so we saw that the 10th partial sum was a lot smaller than the 100th partial sum, which is also quite a bit smaller than the 1000th partial sums. So there's no way for us to justify trusting S10 or S100 even for our last example. They're both obviously very, very bad approximations for our series. Okay, so to control that error, and this might remind you of controlling the error for the trapezoid rule and Simpson's rule, we're going to do some notation first. Okay, so we're going to denote the partial sum, Sn, as summation m equals k to n of our terms, meaning ak plus 1, all the way up to an. But the exact sum is, of course, the limit as n goes to infinity of Sn. When the integral test says that your improper integral converges, then we know that the infinite series converges, that this limit must exist. Okay, so if we only estimate the exact value of S using the partial sum S sub n, then we're missing a whole lot of terms. We're only adding up to a sub n, so therefore, if we subtract the approximation from the exact value, we are missing an plus 1, an plus 2, and so on, all the way to infinity. In other words, summation m equals n plus 1 to infinity of a sub n. Okay, that is of course a positive number. And we don't know what that thing is, otherwise we would know the exact value of the entire sum. Okay, but let's bring back the two inequalities that we saw earlier. We can put them together using a single compound inequality. Flip this over to the left. So am is between integral from m to m plus 1 of the function and integral from m minus 1 to m of that function. In other words, that rectangle is entirely above the function between m and m plus 1, but it is entirely below the function between m minus 1 and m. Different domains. Okay, so now let's apply that inequality to the terms an plus 1, an plus 2, an plus 3, and so on. Okay, according to this, we can integrate from m to m plus 1, so therefore n plus 1 to n plus 2, and from m minus 1 to m, so therefore from n to n plus 1. Repeat for an plus 2 and an plus 3. Okay, and this should feel familiar. We're going to add an plus 1, an plus 2, an plus 3, and so on. Okay, so when we do that, we'll integrate from n plus 1 to n plus 2, n plus 2 to n plus 3, n plus 3 to n plus 4. Sounds familiar? It's the same as integrating from n plus 1 all the way up to n plus 4. And similarly here, it's the same as integrating from n all the way up to n plus 3. All right, so that's what we're going to do later. But let's use, for our notation, we're going to get these partial sums. Let's give it a different name though. Let's denote them as t sub n, where t sub n is summation m equals n plus 1 to infinity of a sub n. Okay, so therefore e sub n, the error that we want to control based on the partial sum s sub n, is the limit as m approaches infinity of summation m equals n plus 1 to infinity of a sub n. Okay, so we're going to add the three terms, an plus 1, an plus 2, an plus 3, just to give you the idea of what's going on. All right, so we said if we add the three integrals on the left, is the same as integrating from n plus 1 all the way up to n plus 4. The three integrals on the right is the same as integrating from n to n plus 3. So therefore, Tn plus 3, adding an plus 1, an plus 2, and an plus 3, is between the integral of the function from n plus 1 to n plus 4 and from n to n plus 3. So now we can go to infinity. Are we ready to go to infinity? In general, our Tm is between the integral from n plus 1 to n plus 1 and n to n. So here's a diagram that explains that a little better. We are going from 5 to n here, and from 4 to 10, 5 to 11 here, and 4 to 10 over here. And check it out. The rectangles are A5, A6, A7, 8, 9, 10. Okay, that's A5 through A10. So those rectangles are bigger than the integral from 5 all the way up to 11, but smaller than the integral from 4 all the way up to 10. Okay, 5 to 11, 4 to 10. So let's scoot down. And now we can go to infinity. The limit as m goes to infinity of t sub n is between the integral, the limit as m goes to infinity of the integral from n plus 1 to n plus 1, and the integral from n to m, also limit as m goes to infinity. But we know that these two converge to the improper integrals from n plus 1 to infinity and from n to infinity. And this inequality might bother you a little bit because n plus 1 is on the left here and n is on the right. And you might say, well, isn't n plus 1 bigger than n? Shouldn't this be on the right? No. And that's because it's not that number. It's the region between that number and infinity. Okay? So if n, let's say, is 10, we're integrating from 11 to infinity. But here we're integrating from 10 to infinity. That's a bigger region. 10 to infinity includes between 10 and 11. So the region that we're integrating here is bigger than the region that we're integrating on the left. All right, so that gives us a bound for the integral test. If we approximate the infinite series using the partial sum Sn, and our series converges according to the integral test, then the error that we produce by accepting that approximation is between the integral from n plus 1 to infinity of our function and the integral from n to infinity of our function. So let's go back to our example in our workroom and let's find bounds for the error in our first example. All right, so let's recap what we had earlier. We had summation 1 over n to the 7/5. We know that that integral converges to the improper integral from 1 to infinity converges to 5/2. So the infinite series also converges. I want to point out something. 5/2 is, of course, just 2.5. Okay? And we already saw that if we took the partial sum up to 1,000, n equals 1,000, we already get 2.94, which is a lot bigger than 2.5. All right, so let me warn you in advance that this improper integral in no way is going to be acceptably close to the exact sum of our infinite series. We don't even know what it is, but it looks like it's going to be at least 2.95. Right? So there's no way we should accept 2.5 as the exact sum of the series. Just warning you. Okay, but we do know it converges. So we saw that S10 is again 2.19. It's even smaller than that improper integral, a lot smaller than the 1000 partial sum. So its error must be pretty big, okay? So let us control E10, all right? So let me make a copy of this because we'll need it a little later. And let's go scoot down to the bottom. Okay, this is where we stop. Let's make a copy. Okay. So that's where we are. Okay, so according to the theorem we just saw, we're interested in E sub 10, right? So it said that E sub n is between the integral from n plus 1 on the left to infinity up to, and at most, integral from n to infinity on the right. So what does that mean? Let's make a copy of the improper integral that we have down here. We're going to make a sandwich. Okay, so we're going to make less than or equal to E sub 10 and less than or equal to something. Okay, so our n is 10. So we have to go from 11 to infinity on the left and 10 to infinity on the right. Okay. So we have the same antiderivative, of course. We already know that it is this. Okay. So we're allowed to recycle that work. We already did it. So on the left, we want integral from 11 to infinity. Okay, so again, at infinity, we're going to get 0, but at 11, we're going to get, so we get 0 minus negative 5 halves times 1 over 11 to the 2/5. Okay, that's not a nice number. So maple, that is approximately 0.95. Ew! So the error is bigger than 0.958. That's almost $1. That's almost 1. That's pretty bad. On the other hand, what happens when we integrate from 10 to infinity? I will recycle up here. If we replace 11 with 10, then this will become 10 to the 2/5. All right. Maple, do your thing. And we get 0.9. Ah, that's almost $1. Okay, so this tells us that E10 is between those two numbers. E10 is at least this much and at most this much. Okay, so we can console ourselves with the knowledge that, oh, okay, my error is at most 1. Big deal. So the exact sum is at least 2.197 plus 0.958, and at most 2.197 plus 0.995. Okay, so can we do better then? Yes, we can, and I'm going to show you how. All right, back to our PDF. So this paragraph is talking about a different example, but it also applies to the example that we see in our workroom. So how are we going to get a better approximation? Well, we said that the error E sub n is exactly the exact sum of the series minus the partial sum S sub n, or in other words, solving for S, the exact sum is the partial sum Sn plus the error E sub n. If only we knew the error E sub n, if we did, we would have S. All we know, though, is that E sub n is between these two integrals, our 0.9 something and 0.95 something. Okay? So if we add S sub n to all the parts of this inequality, then we'll get Sn plus En in the middle. And we'll get this number on the left and this number on the right. Okay, but of course, this is exactly S. So the exact sum of our series is in between these two numbers. Okay, let's draw a picture. Here's the picture. I don't know what the exact sum is, but it's trapped between these two numbers. Let's give them names. Let's call them A and B, because, those are big, ugly expressions. All right. A is, of course, smaller than B. And we know that S is somewhere between A and B. It's only one small problem. There's an infinite number of choices inside that interval. What if S were exactly A plus just a little bit? Or maybe it's exactly B minus just a little bit. Just to the right slightly of A or to the left slightly of B. Okay? So if we pick A as our best choice, then if the correct answer were close to B, we have that really, really large error separating the guess from the correct answer. Okay, so what if you wanted to make a choice which will lower your risk? In other words, pick a number so that no matter what the right answer is, your error will be as small as possible. That choice, of course, is the midpoint of that interval. If you pick that point, then your error is at most the distance from the midpoint to A as well as B, which are exactly the same distance. That distance being half of the width of that interval. All right? So if your interval is very narrow, if it's very small, then half of that width is going to give you a small error. So that is what we're going to use to make a better estimate for our infinite series. All right, we're back. So we have everything that we need on this screen because we know that our E sub 10, our error, is between 0.958 and 0.995. We know that our S10 is approximately 2.1972 according to Maple. Okay, so according to what we just saw, we are going to add our partial sum S10 to all the parts of this compound inequality. Okay, so we are going to add this on the left, in the middle. Do I have enough room? On the right. Okay, but we said, okay, this is S10, and maybe it would be better if I did not spell it out there and said, okay, that's S10. I can add these two numbers and these two numbers. All right, so on the left, let me pull that out so that you can see what I'm doing. On the left, we get that as our sum. On the right, we get this as our sum. Okay, but we said that E10 plus S10, that's exactly S. That's the exact sum. So let's write that down. Thus, the exact sum S, which is these two added together, if we knew exactly what they are, is between these two numbers. This is less than or equal to S and less than or equal to this. Okay, so we can see now that even the 1000 partial sum, I think I just saw it. Where was it? Oh no, I think I left it behind in the previous screen. Did I? No, it's right there. 2.947. That is still a lot smaller than this number. Okay, so 1000 is not enough. We can't even trust S1000. Okay, but this is our A, this is our B. All right, look at the difference. 0.08 and 0.12. Okay, that's about 0.04. Let's make it more accurate. Okay, so the width of the interval is approximately, so we have this minus this, which is approximately, let me scoot out of the way a little bit. 0.03, yeah, it's smaller than 0.04. Okay, so therefore, the approximation that we get by taking the midpoint of these 2 points is going to be pretty good. We can get a better approximation for S by taking the midpoint of this interval. Okay, so S will be approximately, symmetrically, midpoint. Midpoint formula, we will take the average, add the endpoints together, and divide by 2. Add these two. Whoops. I included a character that it did not like. Divided by 2, which is approximately 3.106. All right. So that is a better approximation for our exact sum of the series, which, by the way, nobody knows. We could find the exact sum of a geometric series, convergent geometric series, or a telescoping series. This one is neither. Nobody knows the exact sum of the series. But the width is this much, so the error, the maximum error that we will get by accepting the approximation above is at most half of this interval. Okay, we saw the formula b minus a divided by 2, which is about 0.018. Okay, so yeah, whatever the exact answer is, this is going to be close to it by at most 0.018. So we already know that S could be as small as 3.088 maybe, or as big as 3.124. We'll take the 4. Okay, but by picking the midpoint, we're basically lowering our risk, right? That midpoint is going to be at worst in error by 0.0186. All right, that's our video for today, just over an hour. I hope you enjoyed it. And next time, we're going to take a look at another test that will this time allow us to decide if a positive series is going to converge or diverge, except it's not going to give us a good method of controlling the error of our partial sum approximations. All right, so until then, I hope you enjoy the rest of your day.